Now I want to introduce the concept of a subgroup. If H is a non-empty subset of a group G, then H is a subgroup of G if H is a group under the same operation as G. So let's look at this definition a little bit closer. There are some important points here. So first we have that H is a subset of G. So that's important. That's the first thing that we want to note. The next thing is that H itself is a group. And the third thing is that H and G have to use the same binary operation. So if we have these three things here, then we can say that H is a subgroup. So let's look at some examples. So here is my definition of a subgroup, and here are the three important points. And here's the example we're going to look at. Suppose G is the set of integers under addition. And remember that this notation with the brackets here, when I have the brackets and then the two spaces here, the first thing, that's the set that we're considering. And then the second thing that we have here is always the binary operation, which in this case is just going to be addition. And this is just a way of specifying a group when we have the set together with the binary operation. We don't always need to specify it using this notation, but sometimes it's convenient. And let's let H be 5z under addition. And if you remember what 5z is, so 5z, that's the set that consists of all things that look like 5n, where n itself is an integer. So to write a few of these things out, this would look something like, I'll start at -10, and then -5, and then 0, and 5, and 10, and so on. Okay, so the question is H a subgroup? So we have to check the three important points. H is a non-empty subset of G. Well, it's definitely non-empty. And is it a subset? Yeah, this is a subset of the set of integers. So I can say in this case that yes, H is indeed a subset of G. And so that first important point holds. How about the second point? H is a group. So the group 5z under addition, yeah, we've shown before that that is a group. So I can say yes, H itself is a group. And that takes care of our second important point. And the third important point, that H and G use the same binary operation. What's the binary operation here? The binary operation we just discussed above is addition, and they both use the same binary operation. So therefore I can say that yes, H is a subgroup of G. So I want to introduce a little bit of notation here. We can say that H is a subset of G using this notation. That's something you've seen before. And if I want to be extra clear and say that H is a subset of G, but H does not equal G, then I can write it like this without the little bar underneath the subset sign. And of course you can do this in the other direction too. I can also write things like, if I want to say, for instance, that maybe A and B are related like this, or I can say that B is a subset of A, just having it in the other direction. You can also do something like that. And what about for subgroups? Well, there's similar notation. I can say that H is a subgroup of G by writing it like this, and it kind of looks like a less than or equal to sign. And I think there's no confusion between a less than or equal to sign and subgroup sign, because we're talking about groups here, and so it's pretty obvious from context what we're talking about. And a similar notation applies if I want to say that H is a subgroup of G, but H itself is not equal to G. And of course, I can also do this the other way around. I can write it like this, and that would mean the same thing. So you can use the notation the same way that you would with subset notation. Let's look at another example. So now I'm going to let G be the group of real numbers under addition, and I'm going to let H be the rational numbers that are non-zero under multiplication. So that little star means non-zero. So we can think of the Q with the star here as being the set of all things that are in the set of rational numbers except 0. So I don't want to let n be 0 here. All right, is this a subgroup? Is H a subgroup of G? Well, we have to check the 3 important points. So H is a subset of G, in fact, a non-empty subset. And yes, I would say that this is a non-empty subset of the real numbers. So, sure, I can say, in fact, here I'll write it out. H is a subset of G. And is H itself a group? Yeah, we've shown before that Q star under multiplication is a group. So H itself is a group. And if we weren't sure, we could go ahead and check the 4 group properties for H just to really verify that it is a group. But in this case, yes, this is a group. And how about the last one? H and G use the same binary operation. Well, G uses addition, but H uses multiplication. So in this case, we have a problem. This one does not work. So therefore, I can say that H is not a subgroup of G. So all 3 conditions have to be met, and that's important here because even though H itself is a group, and even though it is a subset, in this case, they don't share the same binary operation, so H is not a subgroup of G. Okay, let's look at one more example. I'm going to let G be the group Z4, and this time I'm not using the bracket notation. And we can do that as long as it's obvious what the binary operation should be. And for Z4, the binary operation is going to be addition mod 4. And H is going to be the set 0, 2. So if I were to write a group table out for Z4, it would look something like this. Remember, this is addition mod 4. And now we can check to see if H is a subgroup. So we have to check the 3 important points. So first, H is a subset of G, a non-empty subset. And yes, 0 and 2 are a subset of 0, 1, 2, and 3. So I can say in this case that yes, indeed, H is a subset of G. And so the first important point holds. H is a group. Well, is this a group under addition mod 4? Well, let's see. If we were to try and draw a group table for it, what would it look like? So we would have a 0, a 2, a 0, and a 2. And 0 plus 0 is 0. 0 plus 2 is 2. 2 plus 0 is 2. And 2 plus 2 is 4, but 4 mod 4 would be 0. Okay. We have closure here. We have associativity. I'll leave it to you to check that. We know it's associative, though. Also, if this was associative, then this should follow that it's associative. What about an identity? Yeah, we still have something that looks like an identity element. And does every element have an inverse? Well, 0 plus 0 gives us 0. That's its own inverse. And 2 plus 2 gives us the identity, so 2 is its own inverse. So yeah, this is a group. H is a group. So that meets the second condition here, the second important point. Last thing, H and G use the same binary operation. Yeah, they're both using addition mod 4. So in this case, since all 3 conditions are met, I can say that indeed H is a subgroup of G. And if I want to use the new notation we had before, I can say H is a subgroup of G. Okay, so there's a little bit of terminology that I want to introduce you to here. We have the trivial subgroup. The trivial subgroup is just the subgroup that consists of the identity element. And if I want to look at the group of Z4 here, in that case, the identity element is 0, so for this particular example, I can say that the group we're talking about here, the subgroup, is just the identity. It's a very boring subgroup, but it counts as a subgroup. It's a non-empty subset. The identity by itself, yeah, it's a group, I guess. Pretty boring group, but sure. And it uses the same binary operation. We also have something called the improper subgroup. The improper subgroup refers to the group itself. So the group itself is a subset of itself, and of course it is a group, and of course it uses the same binary operation, so this is a subgroup. So in this particular case, The subgroup that would be the improper subgroup would just be the group itself, Z4. So again, not very exciting, but it counts as a subgroup. And if I want to really exclude those possibilities, which often you do because these are the boring ones, I can say all the other subgroups would be non-trivial proper subgroups. Those would include all of the subgroups that are not just the identity or the group itself.